Associate Professor here. My name is John Fralick, and I'm delighted to introduce you to accessibility research in the Allen School. You might be wondering, well, what is accessibility research? And specifically, what is accessibility research in computer science and engineering? Well, the premier forum in research publication in this area is called Assets, which was just recently in Galway, Ireland. And they define research in this space as investigating the design, evaluation, and use of computing and information technologies to benefit people with disabilities and older adults. And there's a variety of different kinds of abilities out there. There's different kinds of physical abilities, cognitive abilities, sensory abilities. Even within this umbrella is people who maybe are pre-literate or have low literacy skills. So there's a fairly broad umbrella of the kinds of research that we do in this space. I like to think about two overarching research questions within computer science. And this is more of my perspective, maybe not generalizable to all people who are doing research in this space. But the first is, as computation sort of pervades the fabric of everyday life and becomes essential to partake in society, how can we make computers more accessible to people with all abilities? And then the second part is, as we're seeing advances in sensing, actuation, embedded systems, machine learning, how can we apply these things to make the physical world more accessible? So for example, you might be thinking about how can we use autonomous cars to help people who are low vision, or how can we create semi-autonomous wheelchairs? And there's people within the Allen School who are doing research across all of these areas. For example, there's Maya Kakmik in robotics, Anat Kaspi, who's running the she's the director of the Taskar Center, who's really focused on translational research, or how can we take state-of-the-art research and push it out into the wild. James Fogarty is increasingly doing research in mobile accessibility and chronic illness. There's me. I've been looking a lot at that sort of second question, is how can we use computation to make the physical world more accessible? Richard Ladner, who's been working in this space for quite a while. In fact, as I was preparing these intro slides, and I'm only going to have a couple more, I noticed that Richard's first publication in this space was 1987. And you might have something earlier, but that was at SIGCHI. There's a SIGCHI bulletin on interfaces for deaf-blind, I think, back in 1987. So Richard actually was originally here as a theoretician and began to transition into doing more and more accessibility research, and is kind of seen as a kind of early pioneer in the space. And then Jen Mankoff, who does a variety of different kinds of topic areas in this space, from fabrication to increasing the accessibility of user interfaces. Shwetak Patel applying UbiComp to this space, and Katarina is looking at weird, which is, I guess, westernized, educated. What is the I? Industrialized, rich, and democratic. So oftentimes we're designing for weird, and she's been looking at how we can design more broadly for different kinds of users who tend to be on the margins or periphery of that. And of course, there's lots of different research at the University of Washington beyond the silos of CSE. So this is just a sample. Alan, you did get in there, I guess. So, and Alan also has been an early pioneer in this space. There's people like Mark Harness, who's a clinical professor in rehab medicine. There's people in mechanical engineering like Kat Steele, folks in human-centered design and engineering, and like Jake and Andy, who are in the iSchool. So I suggest you Google them and find out more about what they're doing. There's also lots of industry excitement in this area. Microsoft Research recently started two different groups, one which is led by Mary Morris, and the other which is called Enable. And they're both doing lots of different kinds of research, some of which is translational. They're actually deploying tools like in iOS for accessibility. Apple Research just started an ML plus accessibility group. This is Jeff Bigham. He was Richard's student about, I don't know, 8 years ago, let's say. But he's a professor at CMU now. Oh yeah, and then Xiaoyi is going to be one of their first folks on the team. Yeah, so he's the first talk today. And then you might be wondering, well, where do you publish this kind of work? You can actually submit this to the top places in HCI, so that would be like Chi or WIST. There's also UbiComp or IMWhat, the journal, and then as I mentioned before, there's Assets, which is kind of the top place for accessibility research in computing in general. All right, with that broad, quick overview, we are now going to start our student talks plus one faculty talk. We'll be roughly doing about 8 minutes per person, and so we're going to start with Xiaoyi, who is graduating and, as I said, just got a position. Yeah, go ahead.
Thank you.
Got a position at Apple Research.
Hello, everyone. I'm Xiaoyi from CSE and Dub Group, and I will graduate next month and will join Apple Research, as Zhang just indicated. Today, I would like to introduce Interactiles. It is a set of 3D printed tactile interfaces that enhance mobile touchscreen accessibility. This paper was just published at ASES 2018, and the name Interactiles is from interactive plus tactile. Our research focus is on people with visual impairments, who mainly rely on audio feedback to use mobile apps. When a user moves finger on a UI element, screen reader will read its alternative text. In this case, user will hear shopping cart. When the user swipes their finger to the right, screen reader will write the next item, which will be search box in this case. As we can see, the screen reader translates the 2D UI to a linear audio stream, which loses some information. Previous research used tactile feedback to improve this physical cues as some compensation. People with visual impairments report positively on the accessibility improvement. As you can see, think about this. When you close your eyes, it will be easier for you to use keyboard rather than use a flat touch screen. There have been some efforts to add low-cost hardware to improve accessibility on touch screens, but they are either work only for a single app or work only on large touch screen. So we see an untapped opportunity in this scenario to make it work with many apps and make it work on mobile platform. Now introducing Interactiles, an inexpensive, unpowered, general-purpose system that enhances tactile interaction on mobile platform. Please pass this hardware around. You can feel the widget. You can flip it, but don't break it. I have a backup, so. We identify several design goals from the challenges in previous research. We focus on mobile tangibility, and it should be portable. Also, we want to make it affordable and unpowered so it is easier to deploy. Finally, it should work with many apps rather than just one or two specific apps. Our hardware is a lightweighted 3D printed tactile case with flippable components, which is portable for a mobile phone. And the figure shows a component that can be flipped when not in use, so it won't block the screen. And the 3D printing material only costs $5. The hardware has two major components. One is number pad and the other is scroll bar. A mode switch button can activate 3 different functions of scroll bar, which we will show later in a demo video. User can press or move these physical components to interact with mobile apps. It uses conductive material to pass the touch event to the screen, so it doesn't require power. We spoke with 2 people with visual impairments to design and learn their preferred improvements on mobile touch screen. We improved 4 frequently used functions with Interactiles, which we will show in the video now. User interact with our physical overlay and hear feedback from the screen reader while they're using an Amazon app. And this is the first feature. In the element navigation mode, user can slide on the scroll bar to hear each UI element on the current screen. They can also double click to perform a click on that element.
Caterpillar performance high, add to cart. ONSON anti-theft, add to cart.
So basically it maps all the UI components on the screen to the scroll bar on the right. And the second mode is page scrolling mode. User can slide on the scroll bar to go to the next or the previous page.
Page 5. Page 4. Page 3.
Yeah, again, if without Interactiles, users have to use 2 fingers to swipe, and they don't know exact the page they're scrolling to. And the third mode is app switching mode. User can slide to hear 4 most recent apps and double click to open one of them.
Amazon Shopping, Messages, Facebook, Spotify, Messages, Messages.
And the last feature is number entry. User can enter numbers with physical pad, and which doesn't block the soft keyboard for typing letters. So they can do both typing letter and typing number at the same time.
1, 2, 3, 123, E, T, T, H, J.
And I would like to briefly describe the system concept, how it works, and its compatibility with many mobile apps. The key idea is we insert an interaction proxy between hardware and app UI. This is our work from Kai 2017. It is a software layer that understands the context of a running app and redirects the hardware input to manipulate the app. For example, a user pressed a button on the number pad, and interaction proxies receive that touch event from the hardware. And the proxy handles the event to perform the appropriate actions. In this case, it finds the text box and then append number 6 to it. We create listeners for different input events from physical overlays, for example, tap, long tap, double tap, and long press, and also slide. We also implement those automations that are useful for people with visual impairments. We also use our public APIs, so users don't have to root their phones. The software makes our hardware compatible with many existing apps and screen readers, which I will show now. We evaluate the compatibility of major features on 50 most downloaded apps on Android Play Store. The element navigation function works in 84% of apps, and app switching and number entry functions work in all apps, and page scrolling works in 98% of apps. So it achieves good compatibility among the existing apps without changing their source code. For the user study, we recruited 5 participants with visual impairments to complete tasks and with and without Interactiles. There are 4 tasks designed to test these 4 features. Regarding task completion speed, Interactiles is faster for all users in app switching and number entry tasks. It is slower for all users in holistic tasks. From their feedback, it is because of the learning curve to learn so many functions in a short period of time. For locate and relocate tasks, some participants find it is faster, while some didn't. Overall, participants are positive to Interactiles. All participants like NumberPad. They also see potential values in the score bar. You can see the detailed quotes in our paper. There are multiple future opportunities from this project. I'm going to graduate, so I may not be able to explore those directions, but the researchers who are interested in this area may explore those. The first, it will be helpful to conduct a larger and longer study to understand the learning curve and find ways to improve the Interactiles. Second, we can also enable additional tasks. For example, copy-paste, text editing, and using T9 keyboard. Finally, we would like to support new types of hardware which would like add flexibility to Interactiles. For example, we can add a scroll wheel to achieve infinite scroll on the current screen elements. In summary, Interactiles enhance accessibility by providing tactile feedback with low-cost portable and unpowered system. It is the first mobile system that maximizes compatibility across existing apps without modifying their source code. During user study, we also find it improved speed in 2 tasks and received positive feedback from participants. Thank you. I'm ready for the questions.
We have time for one question while Anne is setting up. Justin.
One of the 2% of apps that it didn't work on, could you broadly characterize why?
Oh, thanks. That's a great question. I don't have the time to cover this. So the app that did, so the compatibility issue is when a screen have too many elements. For example, there are like 100 elements on the screen. It is not easy to map all of them to the score bar while you can still distinguish which you are trying to navigate to. So our solution is we can allow developers to annotate exact element they want to traverse on the screen. So those important elements rather than all the random elements. Yeah, thank you.
All right, cruising right along. So hello, everyone. I am Annie. I am working with Xiaoyi, and my advisors are James Fogarty and Jake Wilbrook, who is in the iSchool. And today I will be presenting on our work in an epidemiology-inspired, large-scale analysis of mobile app accessibility. And I'll break down those different components of that very wordy title as we go. So why mobile apps? Well, they're of course becoming more increasingly ubiquitous and important in daily life, but we know that they contain some accessibility barriers. And the barriers that we focused on were that of labeling errors and image-based buttons. which primarily affects screen reader users. And Xiaoyi touched briefly on screen reader usage, but for example, in the shopping app we have that has a plus icon to mean add to cart, a properly functioning widget would announce add to cart button in audio as someone moved their finger over that button. And that is because the developer has added an attribute called a content description that has that label information. If that code is missing, then the screen reader will instead announce something like unlabeled button, which is obviously creating a barrier to usage. So although we know that there are these barriers in apps, the exact state of accessibility is not well characterized, and that we couldn't really answer the questions of how bad is app accessibility and what are the major barriers. Furthermore, techniques of enhancing apps, such as design and development guidelines and testing tools, really focus on individual apps being made by individual developers. And while we think that's an extremely important component of app accessibility, we really wanted to scope out and reframe our thinking around it to be more holistic of the whole environment that apps exist within. And so we turned to epidemiology to inspire our conceptual framework. One of the key components out of that was this idea of large-scale analysis and the types of insights that you can gain by looking at, rather than one app in isolation, looking at a population of apps and the types of information that we can see in patterns among them. Another idea was this concept of a multi-factor environment, again placing apps within the rich ecosystem that they exist in, looking not only at source code, but considering other factors such as tools, education, and even government enforcement of policy as factors that can influence app accessibility at a large scale. So using this framework as a lens, we approached a set of research questions, and I'm going to talk through a subset of them today. The first being, how frequently are image-based buttons missing labels? And we looked to large-scale analysis in order to answer that. And the second of, how do automated tests in Android Studio IDE address image-based button labeling? Thinking of the tests and the IDEs as tools that are factors, again, in this environment that can affect app accessibility at a large scale. So I'm first going to walk through that first research question, talking about our data set, our analysis techniques, and some of our findings, and then address the second research question, talking a little bit more about the IDE itself and the tests and a couple of the findings we found there. So first, again, how frequently are image-based buttons missing labels? The data set we used was from the RICO project that came out of Ranjita Kumar's group and was published by Decca et al. Last year at WIST. And they had collected about 10,000 free Android apps, primarily for design analysis. And from that data set, we pulled out the view hierarchies, which are essentially the DOM of Android app screens, and are just a list of the elements on that screen as well as their attributes, such as class, which is how we determined if they were an image-based button, and content description, which again is how we were looking at if they were labeled. We filtered the data set to include only apps that had at least one image-based button, which we defined as coming from one of three classes or types of buttons, that of clickable image and that of image button, and these two are used pretty interchangeably and came into the API around the same point in time, and that of a floating action button, which is a newer design concept, a newer widget, and is a slightly more specialized usage. And so that gave us a data set of 5,768 free Android apps, which we analyzed using an analysis based on the Google-released Accessibility Test Framework for Android, which essentially is a set of heuristics seeing whether or not that content description is there. And so we broke our results down into a by app analysis and by button type analysis. So our first by app prevalence, we see along the x-axis we're going to have the percentage of image-based buttons that are missing labels, with lower percentages being better. Along our y-axis, we have the number of apps, again out of 5,768. And our first look at this distribution is it's a very strong bimodal distribution with large peaks at both extremes. And focusing on those extremes, we see that 36% of apps are at the positive extreme, having 0 to 10% of their tested image-based buttons missing labels, but 46%, nearly half of the apps that we tested, had 90 to 100% of their image-based buttons missing labels. So we can really see that this is still a significant problem in Android apps, and one that we should continue to still try to address. looking at this through the lens of by button type, we again broke it down thinking about, does someone's choice of what type of button they're using influence whether or not they're more or less likely to label it? And again, our classes of images are clickable image, image button, and floating action button. And to give a bit more context, these are actually technically subclasses of one another, and that clickable image is the top class, and floating action button is the subclass. But they all use that same content description for labeling. And what we see, first of all, is that there's just differences in the amount of usage that these elements are getting. We saw about 135,000 clickable images and 138,000 image buttons, but only 7,000 floating action buttons, which isn't super surprising, again, given that floating action buttons are much more recent design-wise. But we also saw big differences in their percent error rates, with clickable images having an 86% error rate, image buttons 55%, and floating action buttons 92%. So again, with this large-scale analysis, our big takeaways of answering that first research question was that missing labels in Android apps is still highly prevalent, and it varies by button type, which led us to the question of what are potential factors that might be influencing this at scale. Which brings us to our second research question, looking at the Android Studio IDE lint tests. And Android Studio is the main interface for creating Android apps. And here we see the drag and drop interface in which someone has placed an image-based button on an app screen that has a magnifying glass on it. And we see that that content description is empty, which in turn triggers this automated warning indicating that, so it's sort of a warning both in the corner as well as on the widget itself that indicates that this is an image without a content description and an accessibility concern. And what we found was that clickable images and image buttons triggered this warning, but floating action buttons did not. So again, given the technical similarities, that was a really startling result. So in conclusion, going back again to our research questions, looking at the frequency of missing labels, we saw large-scale analysis as a really good way to characterize this space and found that missing labels are still very frequent. And moreover, that frequency changes depending on the type of image-based button used. And within our second research question about automated testing in Android Studio, first we found that it triggered as a warning, so again you could ignore it and the app would still compile as opposed to an error, and that it was only triggered in 2 out of 3 of the image-based buttons. So these types of insights, although we can't say that conclusively that Android Studio has anything to do with the trends we were seeing in the large-scale analysis, both the large-scale analysis itself as well as really placing it within that rich ecosystem of factors gives us a good motivation and framework for really thinking about how we can enhance app accessibility. Thank you.
Okay, next up is Zhang, who is co-advised by me and Leah Finlater in HC.
Thanks, John, for the introduction. Can everybody hear me? I just want to ask because it's hard for me to hear my own voice. I hope I'm understandable to everybody around the room. Okay. So broadly, my talk is about accessibility for people who are deaf and hard of hearing. So today, I'm going to be talking about 3 projects that are specifically related to promoting conversation accessibility and increasing the general sound awareness for DHH people in the home. So over here, I have 3 projects, a project last year, Hollow Captions, and Hometown. So through this project, our vision together is to change how DHH people think about, experience, and engage with the town. Okay? Let me talk about the first project, the last year project. With this project, what is the problem? Like, what are we trying to do here? As we all know, the deaf and hard of hearing people use visual clues, like for example, the speech or, visual cues, for example, facial expressions or speech reading or anything that are gestures to understand the speech. To use the visual cues, knowing where to focus the visual attention is a very important thing. And deaf and hard of hearing people usually face problems in a group conversation when they don't know where to focus at to look at the speaker. For example, one of the participants in a study said that if one person finishes talking, I do not know who to look at next. That is my problem, because hearing people can hear who the next person is and what they are saying, but the deaf people really cannot do that. So how do we solve that problem? What we did here is we came up with a solution which uses a head-mounted display, for example, a Google Glass, to project the direction of the speaker in the front of the eyes of the speaker. So over here, you can see the arrow telling the direction of where the sound is actually coming from. So let's just see a video of how this whole process actually works. So this is a little laggy. I expected that to happen because of the Windows Mac compatibility. But just to tell you a little bit of detail of what it actually works, is that whenever there is a speaker transition happening, there is an arrow showed on the top of the Google Glass that tells the direction of where the sound is actually coming from. And that the deaf and hard of hearing people can actually turn the visual attention to look at the speaker in this kind of case. So broadly, our research methodology involved creating a huge design space that involved a variety of dimensions. For example, how many maximum icons to show at the same time, whether you want the arrow to be 2D or 3D, or you want the icon to be shown in pulses, arrow, the fingers, a different kind of dimension, and whether how do we actually want to display the loudness of the sound. So there are different dimensions that we explored. So once we explored that dimension with a group of participants, we selected 2 best designs and implemented them as a proof of concept prototype as you were supposed to see in the video. I'm sorry about that, but yeah. So this is a proof of concept prototype that we had with the Google Glass. And after building the proof of concept, we evaluated them in a group conversation with people who were deaf and hard of hearing. So let's see what the participants actually have to say about the evaluation. We don't have the audio? Oops. Okay. Yeah. So as you can see, participants were a little supportive of actually using the Google Glass visualization to look at where the direction of sound actually coming from. So we also have a couple of improvement suggestions and future suggestions from participants we actually submitted in the CAL 2015 publication. So you can look at that if you need more details about that. So it's been a while. So this project was done way back in 2014 when I was a summer intern working with Professor John Prolich and Professor Leah Finletter. And I continued and came back over here to work with them again. The second project is about the HoloLens captioning, which is where we use the real-time captioning projected on, again, in the 3D space of the participant using Microsoft HoloLens. So before I go on explaining the project, I want you to just have a brief idea of how many people in the room are actually familiar with real-time captioning. Whoa, that's more than I expected. Okay, so for those who don't know, you can either ask the people who do know, or you can come in the front and see Eileen, a very talented captioner who's sitting in front of me, and she's transcribing word to word everything that's been spoken in this conversation. So I use that in my classrooms a lot, and for transcription, for understanding what the speaker is saying and what the audience is saying. Right? But the problem with the real-time transcription is that it does not really capture the visual information, all the visual information, like speaker gestures and then lecture material and stuff like that. And usually a person who's deaf and hard of hearing, like me, has to balance their attention between looking at the speaker, the caption, and also possibly the lecture slide. Right? So this multiple information sources causes a lot of cognitive load because I have to switch between multiple sources of information here. That also has been shown to derail learning. And so how do we start that? So what we did is we actually used the HoloLens, Microsoft HoloLens, as a prototype to project the captions directly in front of the user's gaze in the 3D space so that the user can see both the speaker, the caption, and possibly the lecture slide in the same visual way, making them easy to consume information. Okay? So we did 2 separate kinds of evaluation to test the HoloLens captioning. So one was an autoethnographic evaluation, with me as the user, and I tried the HoloLens caption in my classes for a 3-month period. I'm sure like some of the professors over here, for example, James here, have seen me using the caption in the classes, and then he like started like, okay, maybe you're playing a game in my class, like what's going on? You should like stop doing that or something like that. So it's a little awkward when we trying that, but I found that very useful for listening to the lectures at the same time looking at the speakers. We also did another evaluation with in mobile context with other people who are deaf and hard of hearing. And we submitted, both of these works have been submitted to a DIS and an ASHA conference, so you're welcome to look at that kind of paper. Finally, I would go into a little brief of the last project, the hometown project, which is what I'm currently working on. So this project is mostly about conveying sound awareness to people who are deaf and hard of hearing in the home. So like where the sound is coming from, like what the sound is, for example, it's a dog barking, door opening, etc., and what are the physical characteristics of the sound, like loudness and stuff like that. Okay, we already did a formative study with people to know what the needs are, and we're trying to build the prototypes right now, and then we're going to deploy them over longer term, like period of 1 month, in the homes of DHS people to know like if there are any kind of issues that arise with the use of the technology, like privacy concern, information overload, or things like that. Okay. So in summary, what I want to say is that through the project last year, HoloCaption and Hometown, we're trying to increase the conversation accessibility. For example, the first 2 projects increase the conversation accessibility for deaf people, while the last project is mostly for conveying the general sound awareness to deaf and hard of hearing people. Our overall vision through this project is to change the way that deaf people engage and experience the sound. Right. Finally, I'd just like to say that we are always looking for talented graduate and undergraduate students to work with us. So if you care about making the world accessible for deaf and hard of hearing people like me, and also contributing to technology and design field, please do come talk to us. Thank you very much.
And we have time for one question. I have a question. What do you think is the most important property of sound to convey to people who want more information?
Oh, that's a good question. I have to think about that for a minute. Okay, so
Is it direction, loudness, type?
but I think different people would have different opinion on what actually makes the sound more important for them. For some people, it might be that sound conveys information. Like it could be like speech information, could be like information about what's happening around. And the other thing about sound is just like gives you more, how do I say that? It's more the feeling of being there. You know, it's like feeling of consuming all that information. Like you sit in there and you know that the rain is happening outside. It doesn't really like give you a very necessary information, but it's important to like feel like you're actually being alive, being able to take all of that information. I think there's 2 aspects of it, and I think that both these aspects are actually important for people who are deaf and hard of hearing, I think.
Thank you. Let's thank Drew.
Hi, everyone. My name is Qi Sheng. I'm a second-year PhD student here at CSE. And so this work is done with my advisor, Katerina Renicki, and Professor Christoph Gaius at Harvard. So I'm talking about volunteer-based online studies with older adults and people with disabilities. And this work was also published at SS 2018 earlier this year. So recruiting participants can be a challenge for many researchers in the field of HCI and accessibility, especially when you need participants from diverse groups or with certain characteristics. And I'm here today to present you with one possible solution to this problem. So traditional recruiting methods such as finding people from local organizations can be time-intensive and often expensive. Therefore, some researchers turn to those low-cost online labor markets such as Amazon Mechanical Turk, But still, the population on MTurk is not diverse enough, and people often struggle to find tasks that will match their abilities. Okay. So our work is trying to evaluate whether the volunteer-based online experiments with personalized results can be an alternative to recruit and study people with disabilities and older people. So one example of online study platform with volunteers is Lab in the Wild. People will choose a study based on the logo, slogan, and the short description of the test. For example, a person could click on the test to find out how their reading speed compared to others. And then after completing the experiments, instead of like receiving financial compensation, they will receive feedback on their performance. For example, in the reading study, it will show their average reading speed and how they compare to other groups of people around the world. Okay. So in previous work, we showed that Lab in the Wild attract more diverse participants than those lab studies and than those studies on MTurk in terms of age, education level, and geographic distribution. But it remains unknown whether those online experiments with volunteers also attract enough people with disabilities and older people to robustly conduct comparative studies. So to answer this question, we developed and conducted 4 Lab in the Wild studies, and here we show the logo and slogan for each of them. So our goal was to replicate previous work that have been proved to be impacted by certain disabilities, including dyslexia, autism, age-related decline in memory, and in motor abilities. So over 4 to 14 months, a total of more than 350,000 participants take part in the 4 studies, and they range in age from 4 to 99 years old, and more than 7,500 of them are over 65 years old. People self-reported different disabilities such as amnesia, ADHD, autism, and so on. And it's either in the demographic questionnaire if we explicitly ask the questions, or they voluntarily mention them in the comments at the end of the study. So for the sake of time, I will not explain each study in detail. But following the analysis of previous work with our Lab in the Wild study, we found that all 4 studies actually accurately replicate previous results. And additionally, we extend the main findings of prior work with larger samples of specific disabilities and ages. So as an example, previous studies clustered people into discrete young and old age groups when studying age-related effects. Because researchers could only find a few participants in a certain age group. But in our study, we modeled age as a continuous variable, given that we have much larger number of participants from all age groups. So we not only show that the age-related decline is true, but also extended to show that it's true for a much wider age range. So now we show that we are able to replicate and even extend the previous work. But we actually don't know, we noticed that not that many participants with disabilities compared to our entire sample size come to Lab in the Wild and do those studies. So we are trying to understand why people participate in such studies so that we can better develop the studies and design the platform to support their needs. So following a semantic analysis method, we analyzed participant feedback from 6 Lab in the Wild studies and their discussion at external forums where they discussed the test and mentioned having some kind of disabilities. So our analysis resolved in 4 themes. So first, many participants interpret their results in the context of their suspected impairment. So people are often not sure like what functions their disability might affect, so they take those tests to test their boundaries. And related to sense making and using results to test a disability, people also publicly compare their results to others who have similar diagnoses as those external firms. So for example, this person responded to a post about a test related to autism on antisocial personality disorder subreddit. 14 out of 36, they all look the same. Only ones I could tell were when the eyebrows were heavily impressioned. And then another person responded, wow, I got 35 out of 36. I'm surprised because I have Asperger's and find it difficult to read people. So, so for those who are sure about their disabilities, often suspect some kind of interventions could change their performance, so they do self-experimentation to test the effectiveness of the interventions. And you can find more codes from our paper. And so just similar to talking about their self-experimentation results, people often provide context to explain results to the researchers. And we often see their desire for further communication with the researchers at the end of the study. So where to go from here? Because people are seeking feedback from the test, so it's important to provide validated test results. And also, we see people recruit each other at external firms, so we can find ways to involve participants in the recruitment. And finally, we should provide the bidirectional opportunities for further discussion between researchers and the participants. And that's the end of my talk. Thanks.
Okay, time for one question. How did you recruit? I didn't catch that. How did you showed like 350,000 people took Lab in the Wild experiments, which is tremendous. So how did you guys recruit?
Well, for those 4 studies, we basically carefully design the result page, which will provide some information for the participants so that they're themselves interested in the results and then share the links with their friends and then, yes. Cool. Yeah.
Great, thank you.
I'm Nick Bolton. I'm a PhD student in ECE, but I work all the time with Dr. Anat Caspi, who's the director of the Tasker Center at CSE, and I do all my work with computer sciencey things and accessibility. So today I'm going to talk to you about modeling the pedestrian network. Our focus is currently on pedestrian mobility and mobility challenges, so I'm going to talk mostly about those. So as motivation, according to the last US Census, 54.5 million people in the United States can be classified as either using assisted mobility devices or otherwise have trouble walking more than a quarter of a mile. So it's a very large population that could be classified as having some kind of mobility limitation. Now this is a very typical quote that we might get talking to our users. This would be a user who's a manual wheelchair user. The quote would be, using a tool like directions on Google Maps doesn't really help me get around. Actually, sometimes this does more harm than good. I'm sent down streets I can't cross, or up inclines that are impossible to climb. It can be deeply frustrating. So this is a motivational quote to talk about our primary topic here, which is what's the pedestrian reality versus the models that we put up with. Everybody's a pedestrian, but for the most part, when it comes to computers and modeling and even just providing user-facing applications, we don't actually model pedestrians as if they are having their own unique needs and requirements. So I'm going to provide a very simplified example. So how do Google, Bing, Apple, or really everyone who wants to provide some kind of mapping service model automotive traffic or cars? Well, they know where the street is, and they can put you on that street and use that network to route you around. How do they model pedestrians? Well, they just make a couple tweaks. One, they say you are slower than a car. And then sometimes you can go on a couple extra paths, and then ideally they don't put you on a freeway. But that's about it. And then how do they model other groups of pedestrians, people who use wheelchairs or canes or crutches, walkers, strollers, all kinds of different modes of mobility? Well, there's not really any change there. Everybody is modeled the exact same way. In addition, people will typically try to add accessibility to a particular application. Even if they're trying to add a mobility mode, like a wheelchair mode, they'll tend to do something which I would say is grouping people together. They'll do this in advance as an executive decision. They'll say, we want to add a wheelchair mode. We hear this all the time from transit authorities that we work with. So that'd be something like wheelchair equals yes, or wheelchair mode for my application. And that's appealing because it's simple and efficient and you're meeting a demographic need. But it's not an accurate way to actually try to tackle that problem. First of all, you can make large groups. Let's say like a hierarchical kind of grouping thing. On the left side, we could say there's these big groups we could put people into for mobility. We could say they're manual wheelchair users, they're powered wheelchair users. Those two groups have often antithetical preferences, so we need to separate them out. There are crutch users, white cane users, et cetera. All these different large groupings we could talk about. But even within those groupings, there's a ton of preferences and often hard requirements that we would not necessarily have anticipated. So among manual wheelchair users, not all people require curb ramps as a manual wheelchair user. In fact, some people strongly prefer that we don't even tell them about curb ramps when we provide our mapping services, because they think they can just figure out some way to handle it. They'll find a driveway. They'll use some more athletic techniques to get around. There's concerns about safety. That's a very personal decision. You might feel more comfortable going along the street than somebody else does. So fundamentally, there's just a huge set of groups, and you couldn't simplify these into just a handful of radio button options. So Access Map is an attempt to focus on this kind of individualized model of pedestrian mobility based on the fact that it is so diverse to get around. So I'm going to pick on Google. Google is pretty typical, but it's going to be like more common and more approachable. So let's look at Google. We're asking for a route from the University of Washington light rail station up here to EEB or the CSE building. And we get 3 routes. None of them would be considered particularly accessible for someone who's using a manual wheelchair. The primary route that's chosen goes up a gravel road, which would be a deal breaker for some people. And the other 2 alternative routes given both involve stairs. So why is that happening? Well, Google isn't really paying that much attention to things like, are there sidewalks? Are they too steep? Will I run into obstructions? Are there stairs? And when they do model them, they're not providing a particular interpretation for this user. So what would happen if we tried to make a map that did take those things into account? How do we answer these questions? So I'm going to show you first the actual end product and then kind of how it works. So this is a screenshot of the next version of Access Map. It is a web map, just similar idea as Google Maps. It's an interactive application. We both display information about the built environment. So where are there sidewalks? Where can you cross the street? How steep is it? And we also have an automatic route finding service. So you can say, I'm here, I want to get there. What's a route that might work for me? So we prioritize mobility data that is normally missing from this experience. So we've color-coded all the sidewalks by steepness. And we've shown which areas are inaccessible with these dotted lines. You can quickly kind of navigate and get a sense for the space that you're going to be exploring. And you can also ask for routes. So if I say I want to go from A to B, this is going to be a fairly uphill trip. You can see we didn't get the shortest path route. And we can also dial in our own personal settings. So this user has stated, 8% uphill is too much for me. I need to dial that down a little bit. And they have a completely different route. In addition, some more information we might want to be aware of is, are there elevators downtown? This is lore that's passed between individuals who use wheelchairs all the time. Where are the elevators downtown that I can use in publicly accessible buildings? But it's not usually encoded into maps. So fundamentally, how does this work? We need to have a bunch of data that we can interpret into a graph, nodes and edges that have information on them. We need to define an individualized cost function on the fly. As soon as somebody puts in their information, they can say, I need this amount of incline, I need curb ramps, I need to use the sidewalk. And then we get the cheapest path using really standard algorithms. Once you have that approach, you can flip that around and do all kinds of cool graph analytics stuff. So this is showing an example where we've just taken all the subgraphs that you get once you say this user has a hard requirement for curb ramps. So every different little color you see on there is like a little island that would not be something that a person could safely leave if they were not comfortable without using curb ramps. One of the challenges we run into is expansion in open sidewalks. How can we scale? So building an access map just for Seattle, okay, cool. Takes a lot of work, tons of data cleaning, all this offset algorithms. We use machine learning to fix a lot of this data. It takes a lot of work. And that's just for one city. How can we scale this up? And all these questions are up. All the questions you could possibly have about data still exist because most people aren't gathering this data. Where can I get it? How can I use it? Is it any good? How do I collect it? How do I store it? How do I update it? And what we want to do is crowdsource this information. So everybody's aware of their pedestrian space. They can point out what's wrong with it. We just need some way to communicate that into something that's computer readable. The Open Sidewalks project is focused on defining those standards and making it so you can more easily crowdsource that information by having users actually draw that information on a map. And we've had some good success with that. So we've San Jose self-mapped using the tools that we provided. The entire city of San Jose has that mapping now. We've also mapped Bellevue as well as the central corridor of Seattle, which now we have an access map for UW. And we're doing more expansions. So we have a Bellingham coming up, and we're also going to expand to Bellevue and of course, San Jose. Thank you all.
Question for Nick?
How did you get the steepness data for the inputs on roads?
Yes, the steepness data is a derived elevation estimate. So we start with these 3D elevation models that get distributed by the USGS. And then I do a lot of interpretation to turn them into a triangulated network where I'm guessing I'm seeing the actual surface model and not like a random building because that's all like that. But it's all open source as well if you want to check it out or talk to us.
Yeah. Cool. Thank you. We have one quick last talk.
Yeah, I'm not a student. I'm not even looking for students at this point, except for this project, because I'm not going to take any more students. So this is Blocks for All, and this is a project that was done by Lauren Milne, who was my last PhD student. She's now a professor at McAllister College in Minnesota. And so we're trying to overcome accessibility barriers to blocks programming for children with visual impairments. And before I begin on that, I want to say that programming has been around for little children for a long time. And this is a picture of logo. There's a star there, and there's a small little program that says repeat 5 times something to make this star. And it's very visual, and it's accessible to some degree. The text is accessible, but the image, of course, is not. And much later along came Scratch, which is a blocks-based language. And there's the toolbox in the middle, there's the animation on the left, and on the right is the program, and you can drag and drop and create programs and stuff like that. And this is wonderful, and it's really millions of children have done this around the world, probably tens of millions. And it's very, very successful and has a big uptake, but not one blind children can use this at all. So, in this current era, we really want computer science for all. And so let's see what's next. Well, a little improvement maybe is Blockly. And here's the blocks on the left, which are not accessible, and the script, the JavaScript on the right, which is, if you're a little kid, can't really read that. It's too many parentheses and semicolons and brackets and strange stuff on the right. So then maybe this is accessible, but there's no Blockly implementation that is accessible, actually. So so Lauren was sort of charged with how can we make this happen? So what are the accessibility barriers in existing blocks-based programming environments for children with visual impairments, and how can they be overcome? So that was her basic research question. And I'm just going to show you a video and now I might need John's help. I'm just terrible with these tracks things.
Boone, he's very excited about the world. He's up for almost anything.
He's a thinker, and he likes to explore. He's not afraid to do things.
I like computer programming. I might do some computer programming, and I also want to be maybe an inventor, a scientist, and an author.
I don't know, I guess, if it's so important for him to learn coding, but it's important, I feel like, for him to be at least introduced to coding, and then it's his decision to pursue it or not.
I'm Richard Ladner, Professor Emeritus at the University of Washington. I've been observing this movement to bring computer science into K through 12 education. And I've noticed that a lot of the technologies that are being introduced to young children are not accessible, especially for young children who are blind or visually impaired.
I'm Lauren Milne. I'm a graduate student at the University of Washington, and I'm the inventor of Blocks for All. Traditionally, programming has been done with text-based editing, so you just type in your program, which is, of course, very accessible. But more recently, people have been creating these environments for children, these block-based environments that have a lot of visual elements, so they're really not accessible for a child with a visual impairment. We decided to design Blocks for All on a touchscreen because we found that a lot of children, especially children with visual impairments, are already using touchscreens. The screen reader voiceover that comes with for example, iPads is very accessible.
The outputs for the programs were typically visual. There were animations, and those weren't accessible either. Instead of having visual outputs, we have tactile output, which is using a robot.
Drive forward, turn left, and then turn left again.
2 times. If 2 times, repeat, inside repeat, play, button.
Here we go. Oh, no. Really what I'm envisioning is it's really, I see it as a prototype where I try out a whole bunch of techniques, and I'm hoping that other developers who are creating these blocks-based environments can use some of the techniques that I'm finding and make their own environments accessible.
So just a couple of things. I can give a demo afterwards if anybody wants to come down. I have the program right here. And if you're blind, I'd like you to try it out too, because it's usable for them. And this is a picture of the screen, roughly. We're using a touch screen, which is pretty accessible, generally. There's a toolbox on the left. There's the workspace where you write your program. And there's the run button on the right. And the output is this dash robot. So thank you very much. I want to say one more thing, though. There was an Easter egg in that video, and if anybody finds it, I'll buy you a coffee. Okay?
All right, thank you all for coming. Let's thank Richard.